Okay, good morning, everyone. Thanks for coming back. So yesterday I started presenting the message passing neural networks, and so today I will continue. So I just, as a reminder, put the kind of the main steps of the message passing neural networks. So I recall, so we have basically different message passing steps, and at each step we have the molecular graph describing the interactions inside the molecule, and so each node corresponds to one atom and is characterized by the position in R3 of this atom, its charge, and then some features. And so then to go from one step, so here we have small t equals 0, here small t equals 1, and then small t equals 2. So to go from t equals 0 to t equal 1, we have to follow these two steps. So the message passing steps, which says that we, from these features, we construct a message, and so this message basically corresponds to summing over the neighbors of the atom I, some message passing function which has to be learned of the corresponding features. And then there is an update step, which is that to update the features that are here, so the H, we need to compute an update function that depends both on the features at time step t and the message at time t. Okay, and once we have done all these steps, at the end, to get the local energy, we sum over all the different times, all the different steps, some readout function that depends on all the features. So, for example, the local energy for the first atom would be some kind of weighted sum with this readout function of what's here, basically here and here. So we basically look at one particular line. Okay, and so yesterday I started presenting deep tensor neural networks, and so giving the kind of the explicit parametrization of the functions. And so today I will start with the SNET. So this is a message passing neural network that was introduced in 2018 by Schutt and co-authors. And so the way they presented in the paper is, so they see that as a continuous filter convolutional network. And so in the sense, I mean, it's really a message passing neural network. And so but in the paper, it's quite interesting. They make the link between convolutional neural networks that are used, for example, for images and two message passing neural networks. And maybe to give the illustration, because I find it pretty nice. So when you have a picture with you have the different pixels inside it, and so if you just reshape it to have a very long vector, then you can have, like, for example, a feed-forward neural network. So you would have like a very long vector, and then you would have the node and so on, and then you have the property that you want to predict at the end. And so the idea of convolutional neural networks is that if you want to have like many layers, then the number of parameters completely explodes. So it gets very, like, the number of parameters gets too high with already few layers. And so what you want to do is to restrict the number of parameters that you have. And also another interesting thing is that you want to keep some locality of the information. And so this is why, when you define convolutional neural networks, what you do is that you choose the size of some convolution kernel. And so, for example, if you say you want a convolution kernel of size 3 by 3, let's say, you would somehow define a convolution kernel of size 3 by 3. So that's 9 parameters. And then you would, so what would be here, to go from here to here, then you would compute the convolution of the image with all the pixels. So something like that. And then you start again. So it's a bit complicated to write, but basically you move the convolution kernel everywhere. And so you compute the sum times the convolution, and then this is what you get as an output. And then you would do some kind of pooling operations, so some kind of averaging or taking the maximum to kind of reduce the dimension, and also to have some kind of non-linearity, which would correspond in the feed-forward neural network to the activation function. And so in some sense, the message passing neural networks are kind of similar in the sense that instead of these pixels, you have the atoms, and you determine how they interact based on the distance between the atoms. So yeah. Okay. And so in this SNET, so what they have is that the message function is a composition of atom-wise layer. So it's reasonably simple. So that's HI T plus 1 is some WL HI T plus BL. So I will try to highlight the weights, I mean the parameters that have to be fitted. So this WL and BL have to be fitted. And then to define this, sorry, I started with the update step, but I need first the message function. And so for the message function, what they do is that they start by defining by using interatomic distances. So they like Rij is just Ri minus Rj. And then they expand, so they use radial basis functions. So that they call Ek, that depend on this Rij. And so this is just an exponential minus gamma Rij minus eta minus mu k. And so this gamma here is a parameter, and this mu k is a parameter as well. And then the message function, so between sigma I t and sigma j t, is constructed as the scalar product between AJT times WT, taking as input the EK I minus RJ. And this WT is a neural network with two layers, two hidden layers. And with a soft plus activation function. Yes. Gamma and mu are parameters that you just fit in your model, and then at the end you put that in the optimization algorithm, and yeah, you have to fit them.
It's like the expected, you have a norm, or is it just an absolute value?
Here,
IRJ is a scalar, no?
yes, yeah. So it's just an absolute value. Thank you. Okay, and so here I have a. Okay, so here, sorry, you can just erase that. This was, sorry, I made a mistake. So here, this is how the message is constructed, and then actually the update function is just a sum. Update function. So UT is HIT plus the message. So here there is no parameter, and then in the readout function, then this is just a sum. And as in the case of the deep tensor neural networks, it only depends on the last step of the network. So this is sum over I, HI, T. And so I had a question yesterday about how you kind of initialize those features, because you don't really know what to put. So in practice, I was told that they usually put a constant thing. So either all zeros or just ones. And so this is fixed. And so then this is just taken as an input of the next layers. And so since at the end you have to predict the energy, this I mean, yeah, there's nothing to fit here, but it's taken as constant. Okay, and maybe one comment. So here the permutation invariance comes from the kind of the graph architecture, which makes it invariant to permutations, but here the rotation invariance for the energy basically comes from the fact that they use interatomic distances. So if you rotate the system, then those distances won't change. And so you can basically go through all these steps and you see that nothing changes in the calculation. So really at the end, the energy that is predicted is rotation invariant. Okay. Yes.
So is this code then improvement over the deep tensor neural network?
So I would say it's just a different choice. Kind of, yeah. Because, I mean, yeah, somehow you have a very large choice in what you can put in this message function and update function. And then there is the question how long you spend at the same time training. So like when you train just for one set of hyperparameters, then you use stochastic gradient descent and so on. But then there is the question on how well you optimize the architecture itself. And so this may take a while, and so that's why I guess people try different things, and then they get, yeah, they propose kind of a full scheme of message passing neural network.
Maybe a related question. Then how do they validate that this approach? Given the paper, they also include some benchmarks.
Yeah, sure. Yeah, I don't mention that, but yeah, in all of these methods, what they do is that they train this on some given database. So depending on the applications they are looking for, they use different database. But then they train and then they kind of benchmark against other works basically, and yeah. Okay. So now I would like to present another message passing neural network, which is called NeQuip, which was proposed in 2022. So here we are really going to more recent stuff. It's only 3 years old. And so here the kind of the main change compared to the SNET is that so here what the H are always rotation invariant. And so in the NeQuip, what they do is that they also include equivariant features. So somehow if you say that this corresponds to some coordinates in a spherical harmonics basis, here they use only the first one. And in NeQuip, they will use higher order the spherical harmonics. And in practice, they go up to L equal 2. So I think that's the main change compared to the SNET. So capital L will be the maximal L that is used for the Vignode matrices that come in. Okay, and so what this means is that when you rotate the configuration, so you rotate capital R, then you obtain some Vignode matrix H of T of R. And so what this means in practice is that there will be, so then, I mean, sorry, but at some point we get into many indices, but so somehow there will be, so this HT will be decomposed in some kind of HI0T, which would satisfy that it is, so the Vignode matrix with L equals 0. So this is just invariant. And then there will be HI1 of T QR equals H1A1. Yeah, sorry, forgot the Vignode matrix. So that would be HI1 TQR is D1 HI1 T of Q of R. And so here somehow these would be like features of size 1. Like individual features would be of size 1. And here we would have like, if we put them all on the same vector, we would have features of size 3, because we have 3 spherical harmonics for L equal 1. And then we would have the same thing for L equal 2. And so this means that when we rotate HI2 of T, we get D2Q HI2 T of R. And so here we would have, so this would be HI0, then this would be hi1, and then hi2 would be features that are grouped 5 by 5. Okay. And so maybe just as a comment, so in this method, they use 4 to 6 layers of message passing. And so this is quite expensive to evaluate. So that's 6 message passing. Okay, and so now that we have kind of those features, so the way it is constructed, so they're somehow kind of basis functions that are defined, which are so they call that so that would be some g of r y l m a hat, and so these radial basis is learned in the sense that it is represented as a feed-forward neural network. So sigma W2 sigma. Yeah, I would just write it as more abstractly with a neural network with n layers. And okay, and then in this neural network, the activation function. So here, I mean, they make like each method seems to have its own activation function. To be honest, I don't know really what the practical impact of choosing such a like different activation functions. In that paper, they use the CLU, which is so I had never heard of it before, which is x time the sigmoid of x. Okay, and so here then, okay, so then we need the message passing, and so here I will try to write it down. So in the formula in the paper, they have like up to 6 indices in a row. So I will try to maybe write it a bit more abstractly. So the message, if we have features that are our h of t, but then for some L, Li, then we have some Rj, which is the atom we compare it to. And so basically then we need to use, so, okay, so maybe so the idea is that we start from features that are equivariant with some prescribed degrees, so L equals 0, L equals 1, L equals 2. And then we want to generate other features with those same equivariants. And so we want from the different L's to generate, we want to be able to couple them in some way. And so for this, to ensure that the output has the right rotation equivariance, we basically need to include Clebsch-Gordon coefficients. So this gives rise to some kind of large formula. So here we have L-E and E F M F L output and output, and then we have to sum over MF and input. And so here somehow we sum over the neighbors of these G functions. So there can be so Rij, so this is a radial function. They can be, so I put an n here because they can be several of them. And then we have these YLMs Rij hat times the features. So I L I T. So basically here, okay, so this is the already kind of the just this already this small m function. So the capital M function is kind of implicit in this formula. And so the idea is that we start from features with equivariance Li. We want to couple it somehow with an equivariance LF, and then we have to ensure that the output, which we want to be with L output, is indeed equivariant with a right equivariance. Then we need to put the Clebsch-Gordon coefficients here. So these are given and they are not learned. So here, what is learned are basically those functions that are represented with seems to be like neural networks, feed-forward neural networks with a few layers. Okay, and then the update function is the same as in SNET. It's just HIT plus MI of T, and the readout, since we want something that is invariant at the end, we basically, so as in the SNET, they use only the last layer, and on top of that, they only use the invariant features for the last layer. So that would be R equals sum over I, HI, T, but with L equals 0. Something like that. Let me check. I would say LF is fixed, but yes, I would say it is fixed. Yeah. You have, yes, exactly, and then you see the possible couplings basically that are given by this. And so here, what I didn't say is that for this is a kind of vectors of size 2 Li plus 1, and so then you can indeed sum over the mi, which correspond to these different components of the vectors. Any questions on this? Okay, so in practice, yes.
Wait, the aces are equivariant with like rotation, that also means the readout is equivariant.
Yes, so here,
But the energy is there.
yes, that's why you forget about everything, and at the last step you only take the invariant features on the last layer. Okay, and so just to give you an idea, so in practice, I think in the paper they mentioned that when they train it, they have about 2 to 3 millions of parameters. So here, compared to the Beller-Parinello network with thousands of parameters, we have a huge rise in terms of parameters, and so training. So for a given architecture and so on, training the network would typically take between few hours and few days. So that's kind of the rough idea of how long it is to train something like that. Okay, so I have one last message passing neural network that I would like to talk about, which is called MACE. And this is the message passing version of the atomic cluster expansion. So somehow it generalizes a bit the NeckWhip to any body order, and the architecture is also a bit different. And so this was proposed in 2022 as well by Ilias Katasia and co-authors, in particular Christoph Ono and Gabo Chani as well. So it's based on the atomic cluster expansion. And the idea is that they increase the body order, so they increase the correlation order. They increase the order of equivariance here, and how they can somehow couple the different atoms in the system, and then they kind of reduce the number of layers that they need. So somehow what they claim is that they increase the body order, so they increase the correlation order, and because of that, they can reduce the number of layers to only 2. And so this, in the end, reduces the computational cost a lot. Okay. And so here, one way to write the message function is as a body order expansion. So in general, the message function is a sum over j of u1 sigma it sigma jt plus sum j1 j2 of u2 sigma it sigma j1 sigma j2 and so on up to a sum over j1 to j nu u nu of sigma it, and then sigma j1 up to sigma j nu. Okay, and then they go, so I could maybe just write this with G3, because in practice, they go to correlation order 3, which corresponds to body order 4. Okay, and so the way they actually construct this, so there is a parenthesis missing here, is that they construct functions that look a bit like what happens in ACE. So I will write down the formula and then try to explain. Once again, I mean, since we are dealing with equivariance and so on, there are many indices. I'm sorry about that. But then we have, this is really kind of the same structure as for Nequip, in the sense that if we start from equivariant features and we want to keep equivariant features at the next step, then we need to include the Clebsch-Gordon coefficients. And the be somehow in the same way. So here we have a radial function, which is similarly to Nequip, is written as a neural network. Then we have the spherical harmonics. And then we have, so this is different from Nequip. We have a linear combination of the features at the previous step. And 2 of t. Okay. So yeah, so as I said here, we have two things that need to be optimized. We have here the radial basis functions, which would be written as a neural network. And here, so here we have the features with some equivariance property, and then we sorry, that. So we basically couple them all when they have the same equivariance, and so then we have weights here that can be optimized. So it's more general than Nequip, in the sense that in Nequip we didn't have this sum here, but apart from that, this is more or less the same at that stage, except that in Nequip they go to capital L equals 2, and here they go to capital L equals 3 in practice. But in theory, with this you can go to any body order if you want. And so then the way they construct the message is that, so they do they write it as so that's kind of all the components for the message. That's a linear combination on body order correlation, and then they have basically some weights time basis functions, and those basis functions will be constructed from the A's that are here. And so here, those are weights that have to be fitted and then have to be optimized. And then the basis functions are basically sum over some parameters linked once again to the spherical harmonics, and then we have here some kind of generalized Clebsch-Gordon coefficients, then a product, and then the sum of k of some like c t a t a thanks. Okay, so I mean the formula may be not so interesting apart from the fact that when you construct the message, somehow you have a linear expansion. So this is pretty interesting. And the only thing is that in the basis functions, there are things that you learn, especially those radial basis functions. But apart from that, the model seems to be close to linear. So somehow it's kind of a two layers put next together of a linear model where you learn the radial basis functions and where you also deal with equivariance in a systematic way. Okay, and so then also a difference compared to Nequip and Schnett is comes in the construction of the update. So UT is now not just the sum of HT and MT as it was before, but it's a linear combination. So here there are other weights, and so that somehow all the messages have to be can be coupled in some way. So maybe I just write it as W dot MT plus so W T 1 W T2 dot HT, where in the W hidden somewhere is the fact that you need to take care of the equivariance. But somehow before we had just UT equals MT plus HT, and now we have weights that are also put here. And so in the end, the model is also about 2-3 million of parameters when it's trained. And so I guess that I mean in the Schnett it seems that they are in the Nequip, sorry, it seems that they are way less parameters because they're somehow similar, but the number of layers is different. And so I'm guessing that this is what makes the number of parameters roughly the same, in the sense that here we only have two message passing steps, while in Schnett and Nequip it's higher. Okay, and next step, so the readout function is also more general than in Schnett and Nequip. So here the energy is a sum. So I mean so the readout function here, okay, I write it like this, but so we really sum over all the different layers compared to before where we only looked at the last layer, and then we only look at invariant features at each layer. So, and there also are either taken as a linear thing or a small neural network. So that's this. And then EI of t is, I have the space. So EI of t is taken either linear for the intermediate steps or or nonlinear for the last layer. So that's basically our readout function, which depends on this. And this is either some kind of W3, let's say, times hi0 t. And then, so this is if t is strictly less than capital T. And then this is a multi-layer perceptron, so a small neural network for the last layer. Okay, so that's the message architecture, and that's more or less all I wanted to say about message passing neural networks. So maybe one comment on this architecture. So it has been used recently to build kind of a multi-purpose interatomic potential, which is called they call that the MACE MP0 potential. And so this is also Batasia and co-authors. So there are many authors in this paper. And so the idea is that they build an interatomic potential able to deal with any materials. So somehow they want to, I mean, the trend, I would say, in the really recent years is to try to not build a potential that is specifically target to a specific materials or a specific application, but to build a potential that it can be used by everyone for any application. And so here the idea is that, so they in this paper they explain kind of all the cases that they handle properly. And so they don't claim to have like DFT accuracy. So they use DFT data. They don't claim to have DFT accuracy for all cases, but what they claim is that this is a potential that you can use when you basically don't know anything about your system, and you could use that as an alternative to cheap force field that you would use as the beginning. And then when you refine, you will need to train or to use a different potential, but as a first thing, or if you want to perform simulations, that's something that you can use. And I think it's really kind of a trend. So that I mean, this is the overall model for used by Mace. I mean, constructed from Mace, but they are also, I mean, competitors that also are developing their models at the moment. So I think in the group of Michele Coyote, they also have one. I don't remember the name now, but that's kind of what every group seems to be doing at the moment, like constructing their all-purpose interatomic potential.
So in practice, if you want to use this potential, you can download the code and...
Yeah, I guess so. So I haven't tried, but I guess that the code is open and that you can just use it. And possibly, I mean, I'm hoping that at some point, for example, it's coupled with LAMPS so that you can use it in LAMPS if you want, these kind of things.
And to evaluate the potential, so is it cheap or...
So...
compared to a force field, let's say.
So I would say it's more expensive. I mean, compared to like a cylinder Weber potential, it would be more expensive, but it would be. So I wouldn't want to say like wrong numbers.
Less expensive than DFT, right?
Yeah, I mean, it depends. Yeah, it depends on your application because sometimes I mean, if you have really, really big systems and you want to run dynamics, then, I mean, DFT is really completely out of the equation, but also like expensive force fields, expensive interatomic potentials that are based on this model may be also too expensive. So yeah, there is really a trade-off to find.
Small system could be used for bigger systems.
So-
the system with
So it's really, so it's trained on like a lot of different solid surfaces. So it's for materials only, but it's trained on like a database with many different systems. And so, so I would say in principle, you can use this for many, many different things. Yes.
I have a general question on, but at many places, among all the functions, you said that some stuff were learned with neural network, like
Yes.
the MLP or
Yeah.
operator component 4, and some parameters like the W are fitted. You said
It's the same.
So it's also learned with neural
Yeah, yeah, yeah.
network.
And no. I mean, it's not what I mean learned is that when it's a part of the theta in your cost function. So at the end, what you do is you minimize this cost function with which is just somehow the difference between the mean square error. And so what I'm saying when I say that the parameters are fitted or are learned, or then what I mean is that they go into this very large theta, which is in the case of maze is like millions of size 2 millions, 3 millions. And so then you will minimize that based on with your database with some, for example, adding the forces, adding regularization. And so this, you do that typically with a stochastic gradient method.
Yeah, okay, but then it's just you make distinction between like coefficient and functions. So functions will encode them with neural network and then they are learned.
Yes, yeah.
Just coefficients
When yes, exactly. So at the end, this theta is just a long vector.
Yeah.
So then either if you have a function, when I say the function is learned, so it's first represented as a neural network. This neural network has parameters, and so then those parameters go in the theta. So the W and the weights and biases. And then it's just that here, since they're linear, more like in a linear representation, it's more like weights and but it's just exactly the same. And at the end, since you have the layer structure, this the function, the energy function is nonlinear in terms of the parameters, so you have to use some kind of stochastic gradient method to try to find a minimizer for the problem. Okay, and maybe also as a kind of a vague way to describe the new trends. So there has been a huge gain in popularity of the transformer architecture. So that are used a lot by LLMs, so ChatGPT and all the others. And so I think right now people are kind of trying to develop that for this kind of applications. So trying to feed force field with that. So I think one big caveat of this transformer architecture for quantum chemistry is that it's not naturally rotationally invariant or equivariant, and so in the methods that have been proposed so far. Based on this, so there has been several strategies to mitigate the fact that it's not rotationally invariant, and so I think there is so Tess Schmidt I think has a paper on making this actually exactly rotation equivariant. So like modifying the transformer architecture to make it equivariant. So that's one thing. And then there is also a recent paper by Pozniakov and Cheryoty, where they Pozniakov, where what they do is that they develop a transformer architecture which is not a priori rotation invariant, but then what they do is that they let's say average a posteriori, but not like computing explicitly the integral, but just kind of taking samples of different rotations and then summing over that. And it seems that in practice, it's not exactly, so it's not in a rotation invariant or a rotation equivariant up to machine precision, but it's kind of rotation invariant or equivariant up to the precision they have in the simulations. And so they claim that this is fine to have this. Okay, and maybe another thing about transformers is that the actual complexity, if you don't do anything, is quadratic with respect to the number of points that you have. And so whereas for feed-forward neural networks, for example, it's linear. And so when you deal with very large systems, this can be a problem. And so so I think in this paper, what they do is that they use a cutoff radius, and so you pay the n squares cost, but just within the cutoff. So you have basically the number of atoms in your ball to square, but if the cutoff doesn't explode, then it remains fixed. And there is also a paper where they actually develop, they kind of modify the transformer architecture to make it linear scaling. So that's also kind of other strategies that can be proposed. Okay, so I will stop here for the message passing neural networks. So if there are no more questions now, I will discuss the learning wave functions. So going more to quantum stuff. Okay, so here the main questions is how can we tackle the Schrödinger equation directly? So that's the aim is really to kind of minimize the expectation value of the wave function. And so so on Monday I really just presented the Schrödinger equation, and so to start with, kind of as a warm-up, I'd like to just mention a few methods a few classical methods that I used to approximate the solution to the Schrödinger equation. So maybe I'll just write it that what we want is to compute the infimum of the expectation value of the Hamiltonian on wave functions that are antisymmetric. So what n equal 1 to capital N H1 and 3, and then they have to be normalized. Okay, and so one of the let's say most standard method, the first one you learn when you start this field, is the Hartree-Fock method, where the idea is that you restrict the space of wave function that you consider. So instead, so one really important feature about on the wave function is that it has to be antisymmetric. So when we switch two variables, we get a minus sign. So maybe I write it here. So the wave function is antisymmetric. And so this is really a property that we cannot avoid, in the sense that if we want to take any ansatz on the wave function, it will have to have this property. So if we do like psi1 of x sigma 1 to x sigma n, then this is the parity of the permutation times psi x1 xn for all sigma in Sn. Okay, and so the idea of the Hartree-Fock method is to restrict the space of wave functions to Slater determinants, to single Slater determinants. So we first define the set of orthonormal orbitals. So that's write it as W, which is the set of capital phi, which is phi 1 to phi n in H1. So H1 means that the function is square integrable with square integrable gradients. And then, so they are orthonormal. So, okay, and so then the set of Slater determinants is the following. So call it SD. And so this is the set of all functions. So there is a normalization factor in front to ensure that the wave function is has L2 norm 1. And so this is psi1 R1 x1 to psi1 xn psi2 x1 up to psi2 xn, and then all the way to psi n x1 to psi n xn. And so that's the set of Slater determinants is the set of all of these for orbitals that are orthonormal in the sets that I just defined.
So here you work on the domain that is not necessarily R3.
Yeah, I mean, I can put R3 if you want. So, I mean, yeah. It depends what you consider, but just if you look at solids, then you would be on the periodic cell. But I mean, I don't care about this today. So I will, let's just say that we are on R3. And so the Hartree-Fock problem consists in modifying this space here to take the set, the space of Slater determinants. And so we minimize the expectation value of the Hamiltonian, but then only on the wave function that are Slater determinants. And so here, due to the structure of the determinant, naturally we have that if we switch to two particles, then we get a minus sign. So the antisymmetry condition is satisfied. And a very nice feature of the Hartree-Fock problem is that if you write down the first order optimality conditions, then you can actually write down the equations explicitly, and you get an eigenvalue problem which is nonlinear, but you can write everything down basically and get nice equations. So the problem turns to find n orbitals and eigenfunctions and eigenvalues. So I denote them lambda R1 to lambda Rn, which are solution to the following problems. So some minus Laplace plus some potential, and this potential depends on the orbital phi Ri equals lambda Ri phi Ri I from 1 to n. So I won't do any derivation here, and but we can writing down all the steps. So basically, if you look at you compute this expectation value for the Slater determinant, then you get an explicit expression for the energy that only depends on the orbitals, and then you can write on the first order optimality conditions reasonably easily. And so at the end, you have an eigenvalue problem to solve that you can do with classical algorithms, so such as self-consistent field iterations. Okay, but this, and somehow here, one also nice feature is that we trade the high dimensionality of the Schrödinger equation to nonlinearity in the equation, which is posed on a way smaller dimensional space. And then the thing is that when we only have one single Slater determinant, often the solution is far from the exact wave function that we want to find. And so then there are different strategies. So one strategy, which is density functional theory, is to say, okay, so we don't care so much about the wave function itself. What we care about is the electronic density. And so what we will do is that we will say that we have a kind of a set of equations. And so we will modify this potential here so that the electronic density that we get from this problem is the exact density that would arise from the wave function. So in that direction, we completely forget about the original wave function, and we only have orbitals, which then generate an electronic density that we care about. Okay, so I won't talk more about DFT today, but then, so if we actually care about the wave functions, then they are, so the natural extension to Hartree-Fock method are the post-Hartree-Fock method, where you enrich the space of wave functions here. And so natural ways to enrich this space is to add more determinants somehow. And so one first method is to say, okay, so instead of a single Slater determinant, I will consider a linear combination of Slater determinants. And so this is the so-called configuration interaction method. And so this is a linear combination of Slater determinants. And so here there are specific rules on how to select those determinants. Usually they are built from the orbitals, so the solutions to these Hartree-Fock problems. And so then it gives rise to also an eigenvalue problem that you solve using this equation. Okay, and then I won't talk about this, but then there is also the couple cluster method, where you consider the determinants in a bit different way. And so then it gives rise to some kind of some nonlinear equations that you need to solve. And so in practice, this is one of the methods that you can use when you want something very precise, very accurate. Okay, but and so now what I really want to talk about is how you do. So if you want to use a machine learning wave function, what do you do? So in fact, the idea will be exactly the same as what you do in Hartree-Fock or configuration interaction. You choose a parameterization for your wave function, and then you minimize the expectation value of the Hamiltonian. And so the main difference between the methods that I've put here and the machine learned wave functions is that you cannot write explicitly the first order optimality conditions, and so you don't have a simple equation that you need to solve. And so what you do is that you do so you take a wave function that is parameterized with some parameter theta, then you optimize over the parameters, and then you find an optimal value of the theta using, minimizing this quantity. So compared to the method I showed, so on in the interatomic potential, one key difference here is that the cost function is just psi theta HR psi theta, basically. So you say, okay, I want to minimize this quantity. So somehow you don't have data in this. You don't have reference data, you just have a quantity that you want to minimize. Okay, and so in fact, the way people do this is using a variational Monte Carlo. So we'll talk about this, which is not recent. So it's a method that was used already way before these new machine learning wave functions were introduced. So the idea of the variational Monte Carlo method is really to minimize this cost function directly. And so here, basically, to compute this, the wave function is very high dimensional, so it's on R3n, and so you need to compute high dimensional integrals. And so that's one of the key difficulties here, to just try to evaluate this cost function. And so so you need to compute high dimensional integrals, and so the way to do this is namely to use Monte Carlo method. So okay, so so maybe the cost is better written as just the energy. It's more natural. Okay, so so if we forget about the normalization, we can just divide by the norm of the wave function. So so what we want to compute is this expectation value. And so this is the integral over R3n of h psi theta. So maybe since we don't really consider in all of this the dependency in terms of the positions of the nuclei, I will just remove the R dependency, and so we just have an Hamiltonian and that's it. Okay, so we have the h psi, and we want to compute basically this theta divided by psi theta dx. And so the idea here is to multiply to introduce here psi theta of x. And so here we get the modulus square. And here, this psi theta square over psi is a probability distribution. And so then what we need to do is actually to generate samples for this distribution and approximate the integral as a sum over the samples of this value here. So generate samples. So xi using Monte Carlo method. So I will give an example just in a minute. And we approximate the integral as the sum over the sample points. Of this quantity here.
By the number of points.
Yes. And points. Yeah. And basically then once the energy is approximated by this, then to minimize over theta, then stochastic gradient method is used typically. And maybe so just to give an example of a method that can be used to generate those samples. So the Metropolis Hastings algorithm can be used. And so there are several algorithms that exist. So the idea here is that we are given a target probability distribution. Which is P of X. So in our case, the P of X, the probability distribution we want to sample is exactly this. So the model square of the wave function. And then we have some a guessed, so a proposal distribution, which corresponds more or less to a guess, which is written like this. So Q x prime dot x, which is the, let's say, the probability of proposing x prime given a current state x. Okay, and so the way it works is that we start from an initial point. So we choose some x0. And then we perform many iterations. And in this iteration, basically, we generate a new point, and then we decide to keep this point or to accept it or reject it according to some acceptance probability. And then at the end, we're guaranteed that we have sampled correctly the probability distribution. So in the iteration, we first propose a new point. So x prime, which follows basically this, which is taken according to this probability distribution, and then we compute some acceptance probability. Which depends on x and x prime, which is defined as the minimum between 1, and then we have to compute here the probability distribution at the points x prime and x, and then we basically compute some ratio here, and then we accept or reject the point according to this probability. So accept with probability A, x prime. And so what is done in practice here is that often you start for a few iterations and you don't keep the points. And then after a few iterations, you keep all the points. And these are the samples that you collect. And so then you get an estimate of this probability distribution from which you can compute an approximation for the energy. And that's how you, and then you, on top of that, you perform the optimization with respect to the parameters theta that are in the wave function. Okay, so I think it's a good point to stop. Yes. Q is something that you choose somehow.
Yes, it is a function.
Yes, it's a function. So this is something that you choose so that it's easily computable. So
For accepting or rejecting the points is also something that I put in the algorithm.
Yes, so here this is something that would guarantee that you sample the probability distribution correctly. And so basically the way you choose this has a large impact on how many points you will need to sample correctly the distribution. And so the idea is that the more information you have on this probability distribution, the more you should put in it. But somehow, since it's the problem you want to solve, you have to choose something that is in between somehow.
The number of points.
NP is the number of points, yes.
Okay.
The number of points that. Sorry? NB, yeah, sorry. Yeah. It's the number of points. NP, and yeah, it's that's the same. Okay, and so after the break, I will discuss the different ansatz that have been proposed recently for solving this.